The title of our project is Solar Power Management System. The main abstract of our project is the project presents a solar power management system implemented using Verilog, designed to manage the efficient use of solar energy in powering a load and charging a battery. The system dynamically controls the distribution of power based on three key conditions: the availability of solar energy, the charge status of the battery, and the power demand from the load. The project highlights the role of hardware description languages in developing sustainable energy management solutions for renewable energy systems. Introduction. The solar power management system is a critical component of modern renewable energy solutions, aimed at optimizing the utilization of solar energy for various applications. This project focuses on developing a system that intelligently manages solar energy to enhance efficiency and reliability in energy distribution. The core functionality of the system: solar panels, which generate electricity from sunlight; a battery, which stores excess energy for later use; and a load, representing the devices or appliances that consume power. Objectives: to simulate the decision-making process in energy management based on conditions such as solar availability, battery status, and power demand. To ensure that solar energy is used efficiently, reducing dependency on non-renewable sources and minimizing energy waste. To leverage Verilog, a widely used HDL, for modeling and simulating the behavior of the solar power management system. In methodology: 1. Requirements analysis. 2. System design. 3. Simulation model development. 4. Simulation and verification. 5. Documentation. These are the important methods widely used in solar power management system. And implementation. 1. Code development. 2. Simulation setup. 3. Execution of simulations. 4. Analysis of results. 5. Final documentation. Are the various steps to implement the solar power management system. Let's implement by using this in practically. In Verilog code of VLSI, there are two various types. They are design and test bench. In design, module declaration, logic implementation are the structure which is used to build the code. In test bench, module declaration, signal declarations, instantiation, VCD file generation, test cases, output display. These are all the steps to build a test bench. This is the screenshot of EDA Playground, which is a platform used to perform various projects using Verilog codes. There are two separate sites for both design code and test bench code. Here they are featured with Run, Copy, Save, and New on the top left, which is used to run directly without compilation. If error occurred, it stopped and shows error on down. If not, the code run directly and gives the output. On the left side, there is a features of language and libraries. In there we have to edit the features of our code and OVM and UVM types and tools types, etc. based on our codes. Let's come to code. All the code in Verilog starts with module and ends with end module. Firstly, declaration part occur in both test bench and design, and the differences: an on-off condition is under if statement in design, and in test bench it is in single condition with O's and one single quote S concept. Let's go for output. This is the output of the project, which is occurred by waveform. All the features occurs with 0 single quote S and 1 single quote S condition with waveform. If we observe it, we can able to easily understand the output with the comparison of the code. Future scope: integration with smart grid technologies. advanced energy management algorithms, inclusion of additional sensors, expansion to multi-source energy systems, battery health monitoring, user interface development, scalability for larger application, regulatory compliance, real-world prototyping. These are all the future scope of this solar power management system project. Let's see some applications of solar power management system. Residential solar energy systems, commercial buildings, remote and off-grid locations, electric vehicle charging stations, agricultural applications, energy storage systems, community solar projects, disaster recovery, research and development. Finally, we reach conclusion. This project successfully demonstrates how intelligent energy management can optimize the generation, storage, and consumption of solar energy, enhancing overall system efficiency. Through the implementation of Verilog for modeling and simulation, the project allows for real-time decision-making based on varying conditions such as solar availability, battery status, and load demand. The test bench validates the system's functionality across multiple scenarios, ensuring its reliability and effectiveness in managing energy resources. I believe that you understand this concept and thank you for your time.